Yeah, so I'm Justin Hart, and I'm on the faculty of computer science at UT Austin, and I'm part of the core faculty of our robotics research group called Texas Robotics. Texas Robotics is a big interdisciplinary robotics group, but I run a laboratory called the Living with Robots Laboratory, and we sort of chase this central idea of what do we need to do in order to make it practical to see a robot in every home and workplace. And so I'm going to start by sort of telling you a familiar story in the field, which is that in the 1970s, robotics really had its first industrial victory. And that was when companies like KUKA started manufacturing robot arms for use in factories. Um, and the reason this was so successful back then is partly because the sensing and artificial intelligence requirements were basically non-existent. Um, these robots work because parts are fixtured. That is to say that they are mounted rigidly in place at sub-millimeter precision. So if you always make the same motion over the top of it, it'll always sort of do the same thing with the tooltip on the arm. So if you're doing welding or painting or something like that, the robot's going to succeed at that. These robots nowadays run G code or languages very similar to G code, like what would run your 3D printer. Um, and they work in part because they work in these cages. So if you look on the right, there's a robot arm. It's in what's called a work cell. So a work cell is an area that separates the robots from the people in a factory or other operation. And the work cell sort of gives you two advantages, right? One is that it keeps people away from the robots for the safety of the people, because the robot has no meaningful way to interact with the people. It can't detect them. It can't, do anything special. So if a person moves into the robot's tool path, then that person is likely to be injured or killed, right? So you don't want that. And on the other hand, people entering into that work cell introduce complexity. They might bring objects that the robot doesn't recognize or have a way to deal with, or they might unfix your parts or move something slightly. So the state of the world has changed in a way that's unpredictable to the robot. And so now you have this problem of sensing and artificial intelligence, which is adding to the complexity of your operation. Um, but if you look at the sort of emerging frontiers in robots, the things that are places that we're starting to see them, probably the first one that really looks sort of modern is Amazon fulfillment centers. And sort of modern in that this happened 20 years ago, right? So there was a group called Kiva Systems. People had been working on fulfillment center automation, and what they wanted to do is replace the role of a person called the picker. The picker in a warehouse drives around a thing that looks like a big shopping cart. They go up to the shelves of the warehouse, they pick items off the warehouse, and then bring it to a person called the packer who boxes the things, and then they're shipped, right? Okay. What Kiva said is, well, we'll build this like very sturdy robot base that drives under a shelf. It'll pick up the shelf and it'll drive it up to the packer. And then I'll use projection mapping with a laser to indicate which item they should pull out of the shelf, put into the box, and that'll be how packing happens. And so that is a part of how a modern Amazon fulfillment center works. And other fulfillment centers are pursuing other solutions because clearly, Kiva has patented most of these things. And then if you look at the sort of emerging domains, in Austin, we have Fox Robotics, which will take palletized cargo out of semi-trucks and put them into the floors of warehouses. Diligent Robotics, which is UT Austin's spinoff, or maybe concurrent with her job at UT Austin. Andrea Tomaz's company, which has robots doing delivery tasks in hospitals. And then Savioke, which is a spinoff of an older company called Willow Garage, which does deliveries in hotels, room service. And, I've kind of aligned them on this chart. Granted, the axis is a little arbitrary, but, as you go to the left, you look at the older applications, the things that have fewer people and less complexity, right? Like people make the job harder because you have to interact with the people and you have to deal with the complexity of an environment that's dealt for people who are intelligent, right? So it's not structured around the ability of the robot to service the task. And on the right, you end up with more people and more complexity. Robots that are really designed for places that accommodate people. And I kind of put Fox in the middle, even though they're an emerging company, because you can still sort of, you know, um, coerce this task into something that is structured for the robot. So I say that in my laboratory, the Living with Robots lab, that we build robots that understand and interact well with people, and robots that operate in places designed for people. And one thing that we're participating in that's upcoming is RoboCup. RoboCup this year will be held in June. It'll be held, or I'm sorry, July. It will be held in Salvador, Brazil. It's held internationally every year. And when you think of RoboCup, you probably think of something that looks kind of like this. So this is the RoboCup Standard Platform League Soccer. SPL Soccer is played with the SoftBank Now robot, which is a small humanoid robot. And the use of standard platforms, as like everyone's using the same robot, means that we can reduce this to a software challenge rather than a hardware challenge, right? The perception being that, like, yes, you want to make advances in hardware, but maybe a team could afford to purchase a very expensive humanoid, right? And then do better by the nature of the hardware being much better, even if the software was on par. And there are adult teen size humanoid league where there is, you're allowed to bring your own platform. I participate in a different competition that's on site. This is called RoboCup at Home. I'm on the executive committee of RoboCup at Home. So that means I help to plan this competition. I help to run this competition and sort of design the scientific roadmap for it. RoboCup at Home looks very different. It's competed in what's sort of a mock domestic space built out of, cubicle or like sort of like stall furniture like you might see at a convention. But we populate with things like tables, beds, chairs, a dishwasher, stuff where the robot can go through tasks that mimic domestic chores. And so they very closely mimic domestic chores. If you look at the competition, it's divided up into two stages. There's stage 1 and stage 2. All the teams that qualify get to do stage 1. Half of them will be eliminated by stage 2. And the tasks are stated in this very general way. So there's like help me carry, where a person points at a bag and the robot picks it up, and then it follows them through a crowd of people and drops them off at a designated location. General purpose service robot, which is sort of interacting with the robot verbally, asking it to do chores. Receptionist, storing groceries, which is mostly a manipulation challenge. And then in stage 2, much more difficult versions of this. So clean the table, which is taking things off a table and putting them into a dishwasher, so tricky manipulation. Enhanced general purpose service robot, where you're allowed to lie to the robot about what's going on, so it might detect that you've told it to do something it can't do. Restaurant, which happens in a real restaurant. And give me a hand, which is a new task, which is intended to test human-robot interaction capabilities. And then 2 teams go on to a final demonstration where they then compete for the win. There are 3 leagues, but actually one of them has been eliminated, so I should update this slide. There's the Domestic Standard Platform League, the Social Standard Platform League, and the Open Platform League. The Domestic Standard Platform League people like because we all use the same robot, so it's a software competition. Social Standard Platform League, uses the SoftBank Pepper. People like that because there's a low barrier to entry. It's an inexpensive robot. But on the other hand, it has no manipulation capabilities. So a lot of this stuff where it's pick and place, the robot really can't do very well. And Open Platform League is the most popular, which is where teams build their robots and bring them with them. 30 teams performing somewhat comparable tasks. But the SSPL was eliminated this year due to lack of interest. I'm going to show you only a couple of these tasks because I, want to talk about the research. But this is the restaurant task. This is the most impressive task in RoboCup at Home. And I have the audio turned off, so I'll just explain what happens in restaurant. What makes restaurant so exciting to RoboCup and to the league is that for most of the tasks, teams are given 2 setup days prior to the competition in order to map the arena and to retrain any machine learning and manipulation so that it can be localized and prepared to do things in the arena. And it's actually very important because they do things like mark landmarks in the arena where the robot might pick up an object, interact with a person. In restaurant, they're not allowed to map in advance, so they have to use different techniques. This is Gilbert Martinez. He's one of my former students. He's a PhD student at CU Boulder now. He was an undergraduate with me. he's acting as a judge in this context. And what he did is he waved to the robot when the robot was at the front of the restaurant. Uh, the robot looked for the waving person, went up to him, and then he dictated an order to the robot of food items that are at the restaurant. The robot goes up to an area called the bar. There is a bartender at the bar who then assembles the items and puts them onto a tray for the robot or hands them one by one to the robot, which then brings it back to the person who ordered those items and then drops them off. So points are awarded at each step of this, with the most points being awarded if you've completely, satisfied the criteria of bringing the robot, the item over to the person. And there are some things that are very good about this task. Being able to work in an unstructured environment, the mapping and identifying the person are challenging things. On the other hand, there's a lot of stuff that could be improved. For instance, the robot will do this very awkward handover where it's just going to like hold this glass bottle out, and then Gilbert's going to grab the bottle from the robot, and the robot's going to just say, I'm going to give this to you in 3, 2, 1, and open its gripper, right? This is not how people hand objects to each other. And you can also see that every time the robot manipulates something, people are very carefully watching it to make sure it doesn't drop it. So we want that to be better, right? But let's talk about like how we take this and turn this into science. So like I said, in my laboratory, we work with robots that understand and interact well with people, and robots that operate in places designed for people. If you look at how RoboCup at Home is structured, like I said, for most of the rounds, the teams are given 2 setup days to go and map the arena and to do what I call SLAM plus semantic markup. So SLAM is simultaneous localization and mapping. It's the standard technology for mapping in robotics. Most of the autonomous vehicles that you see on the road are doing some kind of SLAM. And the basic version of this is done with a 2D or a 3D LiDAR, a light radar. And it basically gives you a picture that looks like all the areas that the robot can drive that are free of obstacles, right? You can see that the SLAM map on the left does not correspond to the picture on the right. I didn't have the SLAM map from the year I took that picture, but this was the year that the pictures looked the best from RoboCup. So these are the RoboCup pictures I used. And this is out in front of my old office. But if you look at what the teams do, they mark up stuff like these green arrows, like landmarks, like if you want to interact with the cabinet, if you want to take something off the shelf, you should probably stand here when you do it. If you want to talk to people who are on the couch, you should probably stand here when you do it. Any surfaces are marked up because a lot of this stuff is pick and place style manipulation. So you want to know where the surfaces are that the robot can potentially put something down. And then all the object recognition systems are retrained. And you might say, well, why not use like a vision language model or something like that, something more current? VLMs, aren't necessarily tuned to robotics tasks. But the other side of that is also that usually they're large, require internet connectivity, and are slow. And so when we're building control loops for our robots, we would like something faster. So usually we're using something like a local model like Yellow. One of the problems with this is that this approach can't possibly scale up to the real world. We can't do real things the way we do RoboCup at Home. If you need to individually mark up all the locations that someone might care about at all, then that means to do any simple task, you have to say, well, these are all the places you might go. These are all the objects that you might see. You might stand exactly here, here, or here in order to accomplish this. This is how RoboCup at Home works. So one thing we did is on our custom robot platform here at UT Austin, the Building-Wide Intelligence BWI bot, one of the things that we can do is wayfinding. We can have people ask the robot for directions, right? And the way that we originally had that working is we had programmed in landmarks for all the rooms in the building. And then we would just have an undergraduate student drive it to the landmark, say, when you're at office, 2.202 MB, Justin's office, stand here, right? And what we did is I have a PhD student, David Balaban, who works on a task called semantic mapping. And our first approach to semantic mapping was simply to have the robot drive around the building, recognize all the signs, and then mark those locations in its map so the robot knows where to go by extracting the locations visually. The algorithm is fairly straightforward. we're using YOLO to recognize the locations of placards. Of course, we retrain it to recognize the placards that we have. We'll use different plane detection techniques to detect the plane, and then we can kind of flatten it out using a homography transform, read the text off of the placard, and then say, okay, this is the men's room, shoot out 112, right? And then the output of this looks something like this. You know, we can get a sort of you know, top level sort of map that is outlining, you know, sort of symbolically where everything is on the floor. We can mark it up directly in our SLAM map with locations. And then to do this, we used orb SLAM. So we're doing this mapping visually rather than using the robot's LiDAR. Orb SLAM has some challenges when you build very large maps, especially if you're doing it in featureless areas. If you have like white walls around you, orb SLAM relies on orb features, which are extracted from like looking for facets where like two parallel or two perpendicular lines meet, stuff like that. A lot of the hallways in our robotics building are just flat white walls. So we came up with some algorithmic improvements to orb SLAM, which allow us to get accurate maps out of it. It's just not as fast as the original orb SLAM is. And so we said, well, we'd like to do something that looks more like RoboCup at home with this. And so what we started to do is use RTab SLAM, which will give you a 3D point cloud of an area. And so you can see that we can drive a camera through a scene, and we can use RTab in a structure from motion style sense, which will give us a 3D structure. And then what we do is we use the segment anything model SAM to segment all the objects that the robot sees, right? And we're actually able to do some pretty nifty stuff like this. Like if we segment this thing out and, you know, it doesn't really look like a table in the training database, we're not sure that it's a table, we can segment it out globally in the video and say it's the same thing throughout the entire video. And then we're able to use that to retrain our machine learning models. So we can use this as fine-tuning input for our vision models. Then we use an open source version of OpenAI Clip, which will pair a vision embedding to a language embedding, allowing us to identify the objects in the scene. And then we can do meshing, which will give us 3D models, like watertight 3D models that we can then interact with in virtual reality and have labels on top of all the objects in the scene, giving us their 3D locations so we can do things like robotic manipulations. But also, we can interact with them in augmented reality. And this is kind of important because if we want to deploy this at RoboCup at home, and we want to use it to tune on site, we're often going to a foreign country, right? So what will happen is our object recognition models will work great in the United States on a set of objects that we've been using for, you know, 11 months, 11 and a half months, you know, and then the 2 weeks that we're in Brazil, you know, everything is in Portuguese and the objects are slightly different and the video doesn't look the same. And so now our object recognition models don't work the same. With a Microsoft HoloLens, you can go up to it, you can touch the object, you can say this was mislabeled, you can tell it the correct label, and then we have a convenient way to label our training data to send back to our servers at UT Austin, where we then retrain our vision models. So that's sort of a pipeline that we've developed for that usage. This isn't currently in home by the RoboCup, use in the RoboCup at home team. This is something that's still under development in my laboratory, but it was done in conjunction with Cisco Research. So I'm going to change gears a little bit, and I apologize for going fast. I have a lot of material I want to cover, and you know, just long enough to cover it all. But you know, I'll talk a little bit about robots that understand and interact well with people. And this is really my human-robot interaction research. But you know, when I work on human-robot interaction, one thing I always say is that I want to model human behavior well enough that an artificial intelligence system can interpret and project meaningful and gaze and body language in this particular case, but it can act in a natural human way, in this case on a robot, right? The first thing that I really say is necessary to this process is identifying communicative cues that people use. You want to know how people talk to each other, how they communicate with each other. One hypothesis that's been around in the psychometry literature for a long time is that people look in the direction that they're about to walk, which is clear. They look and see if there are obstacles in their path or if they're about to trip, that sort of thing. Um, and that other people look to where they're looking to see where they will walk. So there's predictive power in looking at other people's gaze. And this is part of what is called joint attention. So, that's a hypothesis. If you read it in the psychometry literature, it sort of says this is the thing. But if we want to do this on a robot, we have to be pretty precise in how we define this and pretty precise in what we mean. So we actually ran a human study. And what we did is we recruited a bunch of undergraduate students and we trained them to either look in the direction that they intend to walk, like a normal look, or look against the direction that they intend to walk intentionally. And then we had other people stand by and measure how often other people bump into them. So it's not how often the student messes up and runs into someone, it's how often someone else runs into the student. And so what we found is that if you are giving this incongruent gaze, that people run into you more often, right? Okay, so that's helpful because that means that we validated our communicative cue. And we validated that specifically they're looking at the gaze, because what we did is we also had a version of the study where people looked down at their cell phone and didn't give any gaze cue, and the bumping into them phenomenon disappeared. So they know that that person's a risk because they're not looking where they're going, but if they're looking against where they're going, they're relying on that cue and they're still running into the person. All right, so to test this on a robot, what we did is we actually contrasted against the other popular cue that people were working with at the time, which is putting turn signals on the robot. And what we said is we thought that gaze would work better than an LED cue. The way we did this is we just rendered in Unity, like the Unity game engine, a robot head, and we had the robot head look in the direction that the robot intends to navigate, or we would blink an LED, like a blinker on a car, in the direction that the robot intends to navigate, the same way you would if you were changing lanes on a highway. And then we gave no other help. So the robot is not trying to get out of the person's way, and the robot is always going into what would be the left traffic lane because it's not the natural thing to do in North America. And it's not slowing down or ceding progress to the person. If you watch these videos, when the robot crosses the black line, that's when it makes its signal. You can't see it because it's on the front of the robot. You can see that basically, and we'll let it loop through again, basically as soon as the robot makes its gaze, that is when the person gets out of the robot's way. And on the top, where the robot's using the LED, the person walks directly up to the robot, and then the robot stops because it comes within the safety threshold for motion planning for the robot. And then the person kind of walks around the robot, and the robot continues. On the bottom, we have our Boston Dynamics spot, and what the spot is doing is it's getting out of Parth's way based on his position in the hallway. So it's measuring what lane Parth is in, and it's like, oh, I gotta get out of the way. However, what we would like to do is build robots that can also tune in on that gaze cue. That gaze cue happens earlier than when you move lanes, and we have some evidence of that. And a traditional way to do that study would be to use a Vicon motion capture system. And we do have a Vicon mocap system on site. We could get 2 Tobii eyeglasses. We have 1 pair of Tobies. And then you can get these attachments that make the Tobii work with your Vicon. And you can go through a calibration process and develop some software to say, where's the person looking at? And then we could do the study like that. But what we did is we purchased HTC Vive Pro Eyes, which have an embedded Tobii tracker. And what's cool about this is that it's already an integrated system. Knowing where the person's looking and where they're walking and where all the tracking is comes together. And the cost of entry is like the VR system plus the cost of the computer are all in for the hardware is maybe $5,000, right? Which is a lot of money, but it's not the $250,000 that our Vicon system costs. So that was pretty interesting. But also what was really cool is I assigned a team of undergraduate students to do this study, and they were done with it in 3 months. So if you look at how long it takes to do a typical mocap study, they were able to get going very, very, very quickly. We did have to develop some software in-house because this is designed for video games, and we're doing data analysis on scientific data, but we were successful in that. For this study, the way it looks is that we built this room in virtual reality, and we just said, okay, you're going to start behind A, you're going to walk through A, and then you're going to go to one of these numbers. You're going to go to the number that you're verbally told. And then what we're going to do is we're going to train a machine learning model to know which number you're going at and to determine how quickly we can determine that. And this is how quickly we can determine that. We use a model called the bent wire model. These are Tukey tests that tell us two things. The dashed line is how soon we can tell if you're going to the right, left, or to the middle. So that is the first time that we can tell what direction you're going. And by the black line, we can tell exactly where you're going, right? And so, we're looking at this over relatively short distances. This is a few meters. I don't remember what the exact distance was. It might have been 20 feet. But if you think about when you're passing someone in the hallway, knowing if they're going to go to your left or to your right within that kind of distance is actually super useful. That's long enough to get the robot to sort of politely cede away from you, as opposed to kind of feeling like it's going to run into you. And even though this might feel like, why do we care so much about this? If you look at things like newspaper articles where people are like, delivery robots are banned in this city because they're causing problems, or they're not being used at malls and things like this. This social navigation stuff, this is the thing that's going to enable those applications. This chart just shows which queue we're able to tell, how early which marker you're going to go to. We can see that gaze is the earliest one, and then position is the latest one. So we get the most data, the most accuracy out of gaze the quickest. I want to change gears yet again and talk a little bit about some other human-robot interaction research in the lab. Large language models are very popular at the moment. If you look at, what's going on in LLMs, people want to field them in all sorts of applications. One thing that people wanted to do in robotics and that we're starting to do in robotics is get some practical knowledge about the real world out of a large language model. If you look at traditional robot planning, usually we're doing that in a language called PDDL, Planning Domain Definition Language, PDDL. PDDL requires for us to sort of exhaustively enumerate all the objects in the environment, all the actions that the robot can take, and then we run it through a PDDL planner, and it's great. But what you can do with a large language model is you can say something like, oops, I've made a spill. Tell me the steps that you would take to help me clean it up. And then the robot can list those steps. And then what we can do is we can use embeddings and match them up to skills in the same way we would with a PDDL model, and have the robot execute the steps like pick up sponge, wipe spill, like drop off sponge, right? So this is just a matter of how we prompt the model and how we get the robot to do this. And so we've fielded this robot quite a lot. It's a super popular robot. We use it to give tours of the Anahist Gymnasium, and it is right now not the de facto tour guide, but the computer science department would like if our robot starts to be the thing that gives tours. So what we're doing is we're fine-tuning that tour giving capability so it has like all the knowledge that a tour guide would have. So it's tough to convince your research assistants to exhaustively annotate all the stuff about the building that we're in, because we want to give tours, especially when you're putting them under a lot of pressure to publish papers. But then the other thing is that, we want to then take that and then test modes of human-robot interaction live and deployed on this tour guide. So we have a little bit of IRB type stuff that we're going to work out to where we can test stuff live with real study participants, so we can then, or real, people who are really getting a tour, so we can test human-robot interaction sort of in situ. So here's a video. This is the companion to our Roman paper this year. Roman is one of the premier human-robot interaction venues. This is a demo of the tour guide giving capability. Oops, that was my bad. I accidentally, sorry guys.
Is this supposed to be an audio or
Oh, do you not hear the audio?
no, no.
Oh no.
Yeah,
Okay.
freaking
Well,
text it.
let me explain what's transpiring rather than fixing the audio problem. So Carson, my student, is having a conversation with this robot, and the robot is using a large language model to do a handful of things. One is to generate dialogue to respond to questions, to say, this is the this and this is the this. It's got not a script of what's on the tour, but it has files which describe the environment and all the objects in it. And it carries out dialogue and uses the data provided to it to respond. And that is basically just as files downloaded to the robot, though we're working on adding RAG techniques, retrieval augmented generation, which is a large language model technique, to generate the facts that the robot discusses. It's also using the large language model to decide the behaviors and actions of the robot. And there's quite a lot that the robot can do. One is that it'll drive from location to location. So it'll say, oh, the person's asking about the RoboCup at home area. Let's drive to the RoboCup at home area and discuss this. It can also change the robot's facial expressions. So if it says like, you're telling a joke, or, act annoyed or whatever, the LLM can generate some tags, which can then be interpreted to change the robot's facial expression. Not on that version of the robot. We have one with a face. And so it's really quite a nice system. In addition to all that, it works a little bit different than a traditional cognitive architecture, in that typically what you're looking at is what would be called a sense, think, act cycle, which many of you probably heard the term, where it's like sense, run your cameras, run your localization, think, run your perception, run your planning, act, move the motors of the robot, right? This is all multi-threaded. And it's pretty cool in that the way that it maintains state is it keeps a log, like a text log of all the events that have happened and the important parts of the conversation. And when it wants to reduce the context window to make what it's sending over to a large language model briefer, it'll say, summarize the conversation, describe this person, describe what you remember from this, right? And then I'll send that over, that condensed thing. So what we get out of this is that traditional robot tour guides, because there has been a lot of research in the domain of having robots give tours, like Minerva at the Smithsonian Institute, lots of different robots, the Strands project in the European Union. These robots have these sort of rigidly defined, pools of data they can pull from. And this sort of like, not canned dialogue, but like pretty close to like, this is what I can say and this is what I can discuss. This is all very flexible. You could ask it pretty much anything. It has facts about the building. If you say, don't talk about some silly thing, the constraint is not that it can't at all. It's just try to steer conversation back to the tour, and some of that is freebies from the large language model, but some of that is very difficult to engineer into the robot to make the large language model do something meaningful. And actually what we're doing now is extensions of this, making the robot both more socially capable, but also more physically capable, doing things like manipulations using the large language model. But the basic flow of control works kind of like this chart, where it's like listen and record on a loop, transcribe, do text to speech, make queries to LLM. This all happens on a cycle. When we do planning, again, we're not using a classical planner. We do have a lot of research using classical planners, using like PDDL or Klingo or first order logic to perform planning actions. But in this case, we're actually generating plans using the large language model, at least the top level task selection and execution of the plan. We have a fairly straightforward algorithm for plan validation, where it's like, maybe this works, maybe it doesn't, right? Maybe the plan is out of the correct order, or maybe something about this is impossible. It's just a quick greedy algorithm, but it does work for most of the tasks that we want the robot to do. It's not good in the sense that, for the most part, large language models are not good at what we call like deep planning. That was never really called deep planning before, but because large language models have become popular for this sort of thing, we sort of make this distinction between shallow, which can happen in the context window of the large language model, versus deep, which requires some explicit modeling. And then, it's really fun to have the robot generate these things because, like, you know, this is the memory of the user Carson, who's one of my students, and the robot like uses face recognition and pulls up memories about who you are, so it can continue on your prior conversations or sort of model what you're interested in. And again, we're going into more advanced modeling of this and more advanced like what we would like to extract out of these conversations. Uh, the conversations with Carson are always entertaining because he's usually shooting a demo video. And so it's usually like Carson came in, asked me to do these three things, and then like shut me down and left abruptly. So it is entertaining to read the logs because it's basically a summary of the encounter. Um, I'll skip over this. This is just a flow chart of basically, how the algorithm works. This is, available in our paper on the topic, which is published at Roman this year. And I wish it wasn't quite so animated. But this will just show off the face. The face uses the large language model and is instructed to leave tags in the text that indicate different emotions. This again has some audio associated with it. I apologize that I didn't set up the audio correctly. But like Carson's like, tell me a joke, and then the robot's like happy, and it makes like its happy face while it tells the joke, or it'll make an excited or sad face depending on the emotional context, or what is more appropriately called the affective context, the expression of the emotion of what should be expressed. Right now, what's going on is we're doing a lot of things to generate Python code with the robot as a means of interacting with the world. So this architecture is a major departure from traditional robot architectures, which do those sense, think, act cycles, but they also do a process called world modeling, where the robot sort of says, these are all the things in the world, and it puts it into a planner, and then generates out of a library of things that it knows how to do. This is us verbally telling the robot, we would like for you to do this, and then it writing short programs in a Python API that we've provided to have the robot perform those actions. So here's a quick demonstration of that. This is just a robot, and we said like, or this is version 5 of our building-wide intelligence PWI bot. So this is a custom robot, custom mobile manipulator that we built here at UT Austin. It's like the other robot that we showed you, but it's got this UR5 arm on the front. And we just said, pick up the Cheez-Its from the one table and put them onto the other table. And the robot, wrote code to perform that behavior. So that's pretty exciting. And right now what we're trying to do is to make it generate more exciting behaviors, right? Generate more exciting code. So the basic concept's been demonstrated. Now we're trying to do, more exciting things. And here's just sort of some example code that is generated. So it's like, this is very general because we can say act like a butler, and then the LLM will be like, well, what does a butler do, right? And then we can use chain of thought reasoning to be like, oh, I'm going to serve food and drinks, and then it'll generate Python code to do that, right? So that's sort of the excitement. Right now we have this material in our system for the purpose of code generation. And of course, we're testing it and trying to make it better. But with that, I'm kind of done with what I had to say today. So I guess I'll stop talking and open up the floor to questions.
All right, thanks so much. Yeah, so I also have one question to break the ice. So I saw a lot of these robots. They're like moving around, but where's the code run? Like you mentioned, LLMs or RAGs. Is this something that's running on some servers and then it's being the commands are being sent to the robot, or they are like run on the robot itself?
So we have different ways of doing this. Most of the controls for the robot are being run locally, right? Because you don't want to be connected to the cloud and rely and have that latency. That's like there have been, major cloud robotics efforts and some of them successful, but latency is the real killer in cloud robotics, right? And so for control layers, like people have done it. I don't know if it's the most practical thing to do, but if you have super high speed, wireless, then sure. You know, in terms of our LLMs, this is ChatGPT. So we are using cloud services for that, but we do have versions that run local language models, distilled language models, because they're more responsive and faster, right? And so it sort of depends on the context and what we care about. And the student's, choice, it's actually kind of hard to convince the students that they don't want to use ChatGPT because it gives the best output, you know. Um, but on the other hand, if like in RoboCup at home, they're time trials, right? And so if you're burning time making cloud requests, and that cloud request, there might be like 4 or 5 of them because it's like, tell me the state of the problem. And it's like, oh, you're introducing yourselves to someone. And it's like, okay, say your name. And then it's like, okay. And they said their name's Bob. And then you're like, okay, now I know that their name is Bob. And I put that into my model. And you have like this back and forth, you know, thing. That's a big problem, so those students are easy to convince to use a local model, a distilled model, something that'll give them like pop feedback, right? Um, for other stuff, they may be willing to put up with the latency. They might be fine with it. I tend to really hate latency more than inaccuracy coming out of these things, right? Like it's just like, you're running an experiment and it's dragging on for like an hour, and you're like, man, like just like shave 15 minutes off of this, and that's, but like, you know, when you have something like ChatGPT, which 9 times out of 10 sort of works, that's the excitement, especially when we're doing things that large language models really aren't designed for. I mean, everything that people are using large language for these days is not what they're designed for, right? They're
Yeah,
designed to make good sounding English, right?
yeah,
And so, all this stuff is sort of off the label. But at least some of it's like kind of close to the label, right? And so the stuff that's like really out there, the students really tend to prefer the OpenAI models. But most of it's still being done on the robot. Most of perception, most of manipulation, that stuff's still on the robot.
yeah. I was talking to someone about latency for robotics, and he says like, hey, have you checked what the gaming industry is doing to deal with latency? Because when gamers are playing, they need like fractions of the second latency, so they put a lot of time into figuring out latency, at least to some degree. I mean, you cannot control the networks, but that's something that it's like, yeah, that's a good idea. I should probably check and see what those guys have been. Uh,
Yeah, yeah, and I agree with that actually. I think that there's a lot of room for that. I mean, especially like there are quite a few studies where we are still using stuff that is distributed across the network for whatever reason, right? Limited compute on board the robot, or maybe limited capacity to carry as much compute as we want, or distributed things. And then you're doing it in robot operating system, unpacking messages, or over range. Um, and so, especially in field robotics or outdoor robotics, that stuff comes up a lot. And actually, I often look and have myself said, if we were looking at like what people are doing in the games industry, this would look smoother, right? And then, of course, in games, they have to correct sometimes when something's wrong, and gamers just kind of like shrug it off. In robotics, some of that could be more tragic, right? But usually not, right? Usually, like 9 times out of 10, because you're probably still like driving the robot locally. You're probably not like making like a navigation decision or driving your lidar over the network, right? If
yeah,
you are, then you're probably moving your robot really slowly. And so so there's that trade-off. But I agree. I think that's a fantastic like thing that people have not looked at, but they should be.
definitely, yeah. Um, Have you like, do you know anyone where like, is there any research on like the safety? I know, like you mentioned, like when like the robot gets close, it probably stops, or like, is there like any research or people think really hard about like the safety? Like, for example, like you can, like I was thinking, okay, I'm working right now on designing a robot that's gonna unload the dishwasher. I know that's like very difficult, but I was thinking, okay, like let's say I solve that problem, but then you have like you're gonna have kids, you're gonna have pets running around, like stuff like that, and then even further, if you go even further, then okay, how much should you put? Like, should you even have the robot open to the cloud at all? Concern like there's different concerns with the security, yeah, cybersecurity and all that stuff. So, is anything you can maybe share with us about that you know?
Yeah, I mean that's actually a pretty big area. There are a lot of people at UT Austin who are interested in that. So we can attack that from multiple angles. One is just safe operation, right? And there are people who are concerned with safe operation. There are ANSI standards for cobots. The cobot standards dictate what is perceived as safe hardware for people to interact with. Big parts of that have to do with speeds and torques, momentum, or like proximity to people, or if you're making contact to people, how much force you can do that with, or also sensing in the robot, like force torque on the robot. Um, and so, that's fairly substantial. It's good that people are looking at that because the older standards are sort of based on like um, sort of a default safety thing where the robot's not strong or fast enough to injure someone or separated from them. The problem with not being strong or fast enough to injure someone is it's also not strong or fast enough to be useful often, right? Like if you have like a factory robot or a warehouse robot that's picking up things and it can't pick up like 300 pounds, then why is it in like a warehouse, right? It has to be able to do that. So, good for research and good for the research that was going on 20 years ago, but not great for, 2025. Um, you know, the other thing that people look at is there's a broader AI safety thing, like the alignment problem. The alignment problem can broadly be stated. Um, I think people use this in a very overloaded way, so I'm going to use the sort of atomic precise way that I think is just the only one that matters. Um, and so I would say that the alignment problem is if you have like a reinforcement learning problem, you're learning some like IRL function or some policy on a state space, that what you're learning is what's intended, right? So like like there's these thought experiments where it's like the paperclip making robot and turns the whole world into paperclips, mercilessly killing people and stripping them for resources to turn them into paperclips, and destroying all the crops to turn all the crops into paperclips, right? And so like it's a thought experiment and it's sort of a work of fiction, and yet it illustrates a real problem because you could look at things like reinforcement learning algorithms, and there's a fairly famous video of a robot, not a robot, but an RL algorithm learning to play Hydro Thunder, and because they download old video games and put them in reinforcement learning algorithms, and it learns that it can maximize its score by going through and picking up bonus seconds by going around a whirlpool on a jet ski, right? So it never finishes Hydro Thunder, which is the goal, right? It just gets more and more time on the clock, which raises its score because it keeps on getting this bonus, right? And so it learned something, but it didn't learn what you intended, right? The alignment problem is assuming that there is some value function that we have for what the robot should be doing, and then something that the robot is actually doing, and are those two things in line? Did we program it in the right way? Are we giving it the right inputs? Are we measuring its progress in the right way? And then there's UT Good Systems, which you mentioned the Robotics and Artificial Intelligence Symposium, I think before we started, recording, before I talked. So Robotics and Artificial Intelligence Symposium is co-organized by the Institute for Foundations of Machine Learning Research, the Machine Learning Lab, the AI Lab, Texas Robotics, right? So like really the AI Lab and Texas Robotics. And so, that is, we invite all of our industry partners, and we have a big robotics and AI thing at UT Austin. There's another group, which is ethics in AI, good systems. And the idea is like developing good AI systems, and where good is like the output and the quality is good, or like what it's doing is good for the world, right? And so this asks, those questions in sort of the same way, right? Or like maybe a slightly different way, which is like, if we're interacting with people, what should the robot do? It is asking things like, is this deployment safe because the robot has access to my home, or video data, things like that. And tries to come up with, real world solutions for a world where we're deploying these robots. And so there are efforts like that. So I would say those are sort of the big one. Oh, and then there's one more which I forgot, which is safe and bounded machine learning. So you may be doing reinforcement learning, or you were showing your robot using a transformer earlier, right? particularly in reinforcement learning, there's exploration versus exploitation, right? Exploitation being like I'm using the knowledge of my model, exploration being I'm exploring new state spaces I haven't entered into, right? If you are exploring your state space, you may enter into dangerous states, right? Supposing you have a reinforcement learning model that's learning how to parallel park a car, right? You don't want to strike other cars while it's doing parallel parking. So the bounded safe method for this would be looking at the controls that you intend to send to the robot, the state spaces you intend to enter into, checking them against the simulation or numerical bounds or a planner, and saying, will this come into collision with the other cars or pedestrians or things like that? And then still doing the reinforcement learning to learn how to parallel park, because maybe you learn how to parallel park better than your planner would, but backing up against a planner or a formal verification system in order to prevent the robot from entering into a dangerous state. So that's another.
Okay, cool. Yeah, thanks so much. Other people ask questions. Let's see.
So I heard you said, this is Balu, you said that you're using LLMs.
Yeah.
Those are probabilistic model. They may not generate the same answer every time you ask the same question. So are there any optimization techniques that, for example, moving the robot from one table to another, which you demonstrated in that video, are there any optimization techniques you use for the robots to take the optimized route rather than taking different routes different times?
Yeah, so for the actual path planning part, we use a path planner. So the underlying algorithms there on our robots are the A-star algorithm for the top level path, and then for the dynamics of the robot, the dynamic window approach, DWA. For the actions that the robot will take, those actions are picked by the LLM, but we're not going to the low level controls of the LLM.
Sounds good. Thank you.
Yeah. I see Evelyn's hand raised. Hope I didn't mispronounce your name. I apologize.
Yeah, thanks for this is super cool presentation. I didn't know you is doing so much work on the cutting edge stuff with robotics. I really enjoyed it. Where do you stand on the status of open source models that are trying to understand the physics, the VLA models?
Oh, VLAs. Oh man. Well, I don't necessarily want to take a stance. I mean, I have some advice that I've given in consulting roles, which is sort of private on VLAs. And I have some colleagues who are very interested in VLAs. So like, I guess the first thing, because there's a lot of people in the room, is what's a VLA? VLA stands for vision language action, right? Once you have a transformer model, you can combine multiple modalities in a transformer model by training across cross entropy loss and aligning the embeddings between the models, right? Or training a transfer function between them, right? So like you could have a language model, like just the embeddings from ChatGPT, and then you could have like a vision model, which would also be like a vision transformer, and you could have an action model, which would tell you the motor controls for the robots, right? The one thing I'll say for VLAs right now is that there's a lot of interest in them, right? Because the idea is that you could train something, control the robot. Hello there, by the way. And so you could train something.
Sorry.
Oh, no worries. So you could train something that could do all this stuff with the machine learning technique of choice at the moment. And what's great about these transformer models is it really does make it feel kind of like graduate level statistics to kind of put these things together, right? It feels like PCA, right? It feels like I can map from words into some meaning space and project into that meaning space. I can like take pictures and project into that space and align it and make everything kind of look similar. I can take actions now and do that, right? So then the question becomes like, does this make a VLA practical, right? Vision, language, and action, right? And maybe, the goal there would be that you're able to go end to end and still have these zero-shot transfer capabilities that we get out of these other models, right? That you're able to say, pick up the red can and pick up the blue can, and that will still work. I think that maybe depending on the problem domain, we can see stuff that already works, right? Like if you're telling a car to turn left or right, that's going to work pretty well. The thing that I think makes people excited about this in industry is if you're able to get access to a meaningful action representation, right? So if you're able to get access to like good action training data for your motion model, for your action model, then you're able to say, I have the missing piece, right? Because the language came from the internet, right? Like because we have large data sets that are contrastively trained on giant chunks of the internet, you're golden, right? Or they're not contrastively trained in this case for the language piece, but then for vision, often they are, right? And so then you have like the vision piece, right? And we're able to get that because with contrastive training, I can say, give me the pictures with people in them, and if the word person appears and or doesn't in the associated text, then I can get that. And so I can compare that against images that don't have person nearby. And then action, and the question becomes, where do you get enough action, right? And so what people have been doing for years is you'll have like either a physical arm farm, right, which is doing manipulations, or you'll have something like Isaac Sim, which does lots of simulations in parallel on the GPU to train action spaces. And then you try to like piece this all together, or maybe you source YouTube videos of people doing an action, or some other input, which is getting you the actions, to feed into your model. So the proposition becomes, where are you getting the actions from to get a good action model, right? It makes a nice pitch for a company, because if they have a convincing argument that they have the actions, then they have a convincing argument that they have the missing piece. Does it make a convincing argument that VLAs are going to solve, our manipulation worries? Sort of remains to be seen. I don't really want to take a stance because I have friends who are pursuing this. So if I say yes, then it's like, here's this bet. If I say no, then I'm kind of betting against my friends. And so I'll say that I think that there's a lot of mileage left to cover in artificial intelligence, and that there's a lot of things that transformers probably can't solve, and that data may not always be the bottleneck, right? That we're starting to see the limits of what transformers can do. They're cool because they train very, very, very efficiently on modern GPU hardware, right? Multi-step planning, stuff where we have a sequence of actions, being able to download that entire sequence of actions to the GPU and do training epics like that, rather than go back, evaluate the steps of the plan, and then feed that back in that recursive loop that you used to have to do. That's like a 1000x multiplier in the speed that you can train these models, or larger depending on the context window, right? So the question becomes, was the problem the context window, or is it what we're trying to learn, right? And so, yeah, maybe a little bit of both. Maybe 6 in one hand and a half dozen in the other hand. I would say that probably it's not going to solve everything, but probably we'll see a lot of good stuff come out of VLAs. But we probably won't get to where they do everything we could ever want to do, if that makes sense. Like we'll see neat stuff, just not.
Yeah, I
not
appreciate
everything.
that. Yeah, I see. I can see how you're kind of hesitating to give a definitive answer, because there is a bunch of experimentation, and it feels like VLA should be advancing a little bit faster. If you look at how LMs were advancing with text, and they seem to be kind of spinning their wheels a little bit. All sorts of diffusions and other experimentation, like variations on transformers. And then Andrew Karpathy comes with that announcement that killed the LLMs when it comes to physics. So I don't know if you have something that you want to publicly express an opinion on that.
I think that what VLAs have going for them is capital and investment. Because people want this, and because people know that they can make money off of it, there's a lot of money in there, right? And, certainly very smart people are making plays in this area. And I mean, I have thoughts, I think that if you're able to constrain the problem domain enough, you can probably learn a meaningful enough model, right? But I think it's a matter of like constraining the domain down to where you can learn the model, right? Even with language, like I always felt like when Chat GPT first came into when I had my first access to GPT-3, maybe GPT-2, where it was, I was like, I wonder if I can just get this to generate copyrighted material for me. And then I just like put in like the first few words of a song and I get the rest of the song out, right? And I was like, okay, what's going on under the hood is what I expected. This is the output that I expected. And then, companies like OpenAI were like, okay, we can't have that. So they put in they put in a guardrail to prevent that thing from generating that exact text, right? Or they turn up the temperature on the generation to prevent it from generating exact clones of what's in its model. And then people came up with jailbreaks for that and attacks that would allow you to do that. And then they were like, okay, we got to detect those attacks. And it's unfortunate because I used to say, draw me, and then I would just like smash the keyboard like this, right? And then it would draw me random scenes of like whatever that nonsense generate the embedding of, right? I didn't have to describe it, but I would always get an interesting picture, right? But now it's using a chain of thought reasoning process that completely defeats my ability to just like provide it with a nonsense thing to generate an embedding to give me something new, right? And so like that productization process, makes it feel super good, and it is super good. But it also points out the limitations of what it can actually accomplish, right? And so, but I actually think the challenge with action is something different. The challenge with action is that you can get internet scale text and you can get internet scale speech data and you can get internet scale image data. Internet scale action data is not available, right? And so there isn't a ready database of information that'll get you there. But even if there was, I'm not sure that the LA would do it, But again, like, I want to be very careful in weighing that and saying I'm not sure, because again, friends of mine are doing this. I don't want them to watch this video and go, you said that my research isn't going to work, which is not what I'm saying. What I'm saying is that you can probably make some versions of VLAs work, right? Can you make something that feels as awesome as ChatGPT does? I think that the real answer there is that large language models don't feel as awesome as ChatGPT does. They've coerced those large language models a lot with a lot of like very specific training data and stuff that they're doing on the back end to make the output look very coherent and like it's giving you good advice, But if you ask it something that hasn't like really been super fine-tuned on or isn't, backing up in some way, it's going to start to generate some nonsense very quickly. A good example is uh, uh, last weekend, I helped a couple weekends ago. I helped my girlfriend install a thermostat in her recreational vehicle, right? And like once it got down to I don't have this model, this manual. I didn't train on it. Nobody has fine-tuned me on heating, ventilation, and air conditioning. No one has worked me through electronics. It starts generating text that sounds right, that if I listened to it on the surface, it might have killed me. So at that point, the information gets bad because they're super fine combing over millions of conversations to say the correct answer to, can I, make a cheesecake like this is the recipe, right? And so when we get into action, you need that sort of fine tuning, which will probably be really great if you're like deploying it in some small thing, but if you want it to be in a super general state space and you start asking it like, fix the plumbing on my toilet, it's going to start to do things that you don't want it to do, because those fine tunes have to be taken to make to make, nobody should ask ChatGPT legal advice. But when they found that people were doing it, they started to fine tune on all the questions that people were asking, right? And so then they get out good sounding legal advice. But if you just trusted a transformer to do that, wouldn't be very good at it, And so that's, I think, why people in the field are starting to look at what comes after transformers. But the problem with what comes after transformers is I don't think anyone has something that goes onto a GPU as efficiently, that can crunch as much data and get as many training epochs for sequential data as transformers, right? And that is, it's not a huge problem because transformers are awesome, but what it is a limitation that we have to overcome to get past transformers to get better performance,
Yeah, I totally agree with you there. Where like I believe like probably like there's gonna be some applications where like limited applications where it's gonna like it makes total sense to have something that has been fine tuned. Like I saw some demos where there are two robot arms and they're like folding uh, um, napkins or something, like folding towels. So that would be a perfect application for like hotels, right? Where you have like hundreds of towels. So you can start with something that doesn't have to be generalized. So like that doesn't have to be like super generalized, but it's still super useful in particular areas. Like you cannot. I mean, it's still like kind of amazing that like I saw this paper say like only like 800 towels with no problem, and I forget how many hours. So things like that. I believe that it should be like you'll have this application. People are probably going to make a lot of money just based on like more like restricted applications that can be repeated over and over before we can get to something more generalized that people are eventually going to look for. So, and that's why I feel like probably something like a VLA, probably people are going to still find like super useful applications, but
Yeah.
in a narrow domain. But yeah, but they don't like if you're like a hotel, if you have a table with two robot arms and then you just throw a bunch of towels in a few hours you have them all nice and packed and they don't have to hire a person for that. That's a huge bonus, right? So how many hotels are in this world? There's a lot of them.
Well, and also with stuff like that, in that particular domain where it's deformable manipulation, right, and
Yeah.
deformable transforms, everything that we really know how to model well is rigidly transformed. There is stuff that's done on deformable manipulation, but there, to the best of my knowledge, there aren't like textbooks on deformable manipulation because like the modeling just isn't quite there yet, right? And so, and yeah, you can run like some like finite element analysis like type thing, but it's still not great for motion planning or manipulation planning, right? Like where your grasp points will be and the behavior of the thing when you try to fold it. For motion planning isn't really there yet. And so yeah, like a VLA can be really great for that, right? Because if you're able to give it demonstrations where it performs those manipulations, but it may also not be a VLA at that point. It may just be like sequential learning of the task, and then you're learning like grab the towel here and do the manipulation and do like an RL sequence that will produce the result without modeling the fold behavior, right? And so there's quite a lot of that would be up to conjecture there in terms of like how you would accomplish it. But you could treat it like an engineering problem that you could solve at this point, Yeah.
Any other questions? Give it a second there. All right. Well, thanks so much, Justin. This was awesome talk and a lot of things.
Thanks so much. I think I've done 3 for y'all, and I've always had a good time. So I'm always happy to come back.